else that you attach, then that else is paired with the if, and then it does it, and then.
Yeah, so I think it falls out naturally.
Yeah.
And we agree on a unique parse tree. Even though one could create two parse trees, we agree on one of them. And we process it based on that one.
So you just take the, basically what I'm saying is you just take the, basically for the lowest if, then you check whether then the else is paired with that, and if there's not, then you're not actually gonna have a situation where, with that, where you say that if doesn't have an else, but then the other one does, because it's either there or it's not. Right?
Yeah, so it's all good, it'll work out.
Yeah.
Brandon?
So would a parser not evaluate the scope of the if it does or does not have curly braces?
You don't really need to evaluate the scope of the ifs. With the recursive, you're in the same production rules for all of the if statements. And so the recursion actually handles the depth of the nested ifs. Okay, so, moving right along. We have today, that's the 22nd, and project 2 is due on March 1st, which we see is next Thursday a week. So I figured you all probably are beginning to think about it a little bit now and maybe consider writing some code or whatever. And of course, I can be facetious and sarcastic, right? Well, so, last fall, I've been thinking about this for some time. And last fall term, I wrote and demonstrated a piece of project 4 for the class. And I intend to do the same thing. I mean, I already got it written, so I'm going to do it for you as well. And I didn't think that it helped them much, but maybe it did. I mean, I didn't get much feedback on it. Well, so I got up this morning and I said, I ought to adapt that program that does project 4 for project 2 and show you all the parser. And so I did that this morning. Well, and so I messed with it I had a couple hours. And I said, well, this ought to be really simple. All I got to do is strip out the stuff. Turns out it wasn't all that simple, but I think I did it. And so, unless you all are going to yell at me if it doesn't work, because I just thought of it, and given that you're working on your projects now, I mean, if you haven't started them, you're in very nearly panic mode. And so, I don't know if this will do you any good to speak of, but I did it anyway. And we can look at it briefly. And so, I've got my parser demo. And so I think I updated the readme. And so my parser will parse this grammar. But of course that grammar is left recursive. And so it parses this grammar, which is the fix or the lack of left recursion of that grammar. And so this grammar that I've given you here is the arithmetic expression component of the C- grammar. That is exactly what C- gives you. It gives you in about, well, it gives it to you left recursively, but your fix looks very much like this. except of course you've got subtract and divide rather than just add and multiply. But nevertheless, you want to fix it in this way. And so I have my parser, and I wrote it in Python, and I've got output files, which aren't actually output files, they're input files, but I call them out anyway because I was thinking about it as being the output of the lexical analyzer. And so if we cat out, I put each token on a line. So A plus B star A, dollar delimits the end. I could have used end of file, but dollar was easier because that's what we do in class. And so these are the tokens that Emily wanted to put into her output file as a result of her lexical analyzer. And her parser then is simply reading this file. And so my parser, Python, reads the output file, and so I did this morning, and so it all worked perfectly, except it accepted everything. So then I said, oh, that isn't any good, it can't accept everything. So I have those out.bad and out.bad1 and out.bad2, and so I fixed it so it rejected the output bads. And now it rejects everything. Well, when I thought about debugging it in class, thought that might be instructive. And I didn't really want to debug it in class because then you're all going to sit there and wonder what in the world I'm doing and so on. But I see that I now get to debug it in class for it should not reject, and didn't reject until I did this. So I will momentarily debug this in class. And so that's what I've got. So compilers, my parser stuff, my parser.py. All right, and so we see what's going on. Well, so how does it go? So I read off the command line. Line 10 allows me to read off the command line. And so I have A plus B star A dollar. So at the bottom is the main routine in Python, at least the way I wrote it. The bottom, the main routine, and the main routine calls function E. So function E calls function T. Function T is not on the screen. Or was it? Yes, function T now is at the top. Function T calls function F. Function F says, if I see a left paren, that's good. If I see a right paren inside that, else if I see an A, so toke has my current token, that's what I read in. So F accepts the A, and so F returns to T. Well, maybe this is too hard to work. All right, I'm losing interest. You want me to debug this? I'm losing interest in debugging that. I actually think, see what's happening, it says reject in N. And so it printed line 44. And so line 44 is actually saying at line 44, the line 43 says if the token is not equal to plus. Well, it's not equal to plus because it's equal to $sign. I'm at the end of the string. And so this if statement at line 43 is what's bad. I don't see a plus, I see a $. Now plus is in the follow, well, that might be what's screwed up. That might be what's screwed up because that N, I think, should go away. And so if you look at the README file, see, that if should say this. All I've got is plus in it, and the N wants to go away, and so a good token for N goes to empty. See, N can go to empty, and so a good token isn't just plus. A good token is $ plus asterisk and paren. If the next token is any one of those four, N goes to empty. And so that's what's wrong with it. I only ask for plus, and I need to say, if it's any one of those, it's still good. Make sense? Well, so first and follow are important to decide if the parser can continue. So again, I was nervous about this. I didn't have it tested and debugged as nicely as I should have, but well, so here's my Python program. It starts right here. It reads in the first token. It invokes function E, and so then function E invokes function T, ultimately invokes function M, function T invokes function F, and ultimately function N. Function M accepts a plus and reads the next token, and then invokes function E and function M. And here's where I ask if M goes to empty. And so that's the follow set, and I didn't put in enough symbols for the follow set. And so function F accepts, well, so you can see again that the program is mimicking the grammar. And so I claim, I ran out, and I claim if I change this to a plus, which is in the follow set, now I claim, at least I hope, my parser without my parser.python still rejected it. Well, that's because it didn't find the $sign. You got to find the $sign as well. And so it's got to find if the token is not this. So I got to write an OR. So I need the plus. I can't write an OR in Python off the top of my head.
Or this is you want the logical OR, and it's just OR, the word OR.
So if it's not equal to a plus,
Or,
or,
yeah.
not equal to a dollar sign. And when I read it in, I get the new line as well. So if it's not equal to a plus, well, it's not going to be equal to 1. And so it's going to print a reject. And so I don't want or, I want and. Right? That's the logic I want. Well, so the next token, if the next token is a plus, I don't want this to happen.
That's always gonna be false. That and right there.
Yeah.
It's always gonna be false no matter what. So you can't do two things.
No, it's not equals. It's,
Yeah.
oh,
It's
the more
not
is-
equal to either.
so if it's not equal to that, and it's not,
It's not equal to a dollar.
So if it's any other symbol than a plus or a dollar, I want to reject. Is that what I'm asking?
and if you say or, it's not, it's always going to be true because it has to be one symbol and it's either going to be not one or not the other. So yeah, the and is.
So it should be or?
No, you need I was saying that or
Should be
doesn't,
and?
or doesn't work. You need, yes, and is what you need for this.
Well, so toke is a dollar sign. And so this is true, and this is not true. This is false. So the and is false. So it wants to be and. You look at comp structures, you know how true they is and stuff like that. And so is this syntactically correct? I can't believe this is syntactically correct.
Also took symbolically.
All right.
Accepted. Done.
So that, this now is the, now, so your projects should run like this. Don't print this. Do not print its trace. Your project should print this. And that's it. I had it print this so you could see where it went. This is designed to be instructive. Make sense? Does that help? You can be honest with me and say, nah, you're wasting your time. Nah, you're wasting your time, this didn't help. It was fun for me to do though. Questions?
This might be a bit off topic, but I don't know Python, but how does it know when the two if statements in M, for example, how does it know that one if statement isn't, the lower one isn't inside the other one?
Basically.
The if on line 32
Yeah.
is inside of the if on line 27.
Oh, wait, I see. I get
Python groups by indentation.
it. Okay.
And so the fact that this if is at the same indentation as the print and the E and the M and the token stuff makes this if inside of the if that starts on line 27.
Okay, but then when M, it could go to, it shows that it handles plus E M, but then what happens if it goes to empty and then the follows, and then shouldn't it be searching for the follow set in another if statement?
Well, so there's more that should be there. If the token isn't a plus on line 26, then the whole if fails and the function falls out the bottom.
Okay.
It just simply totally falls out the bottom.
Okay, so if it doesn't see that, then it assumes there's the follow set and goes up, and then it'll mess up, and then it'll just fail somewhere else because the next thing because the thing that follows isn't something that's supposed to be there.
Yeah, well, it returns to where it came from.
Yeah, I see.
Well, let's talk. Let's talk in my office if you want to.
No, I think I get it. It's just that mine checks the follow set in every function where it can go to empty. It's just it didn't do it in this one, but I think that's fine. Yeah.
Just sitting, waiting patiently, right?
That's right.
Me too, I'm just waiting for everybody to quit talking. If you all quit talking, I'll start talking again. But you may very well have more important things to say than me. All good? And I'm not being sarcastic then. I don't mind being sarcastic, but I wasn't then. Well, so hopefully that helped. And if you'd like to look at it further, I don't have it in the public directory, but I am willing to put it in the public directory. But I'll only do so if you ask for it, because if you don't ask for it, then you don't care and it wasn't helpful. If you think it might help, you do care, then you get to ask. And so that's a signal to me.
Please do it.
It is the little block of code that you should code to process arithmetic statements. Now, it's not all of it. You know, you're going to see things like x is equal to y plus z times parenthesis m plus n paren. Well, and so my little program will process all of this stuff correctly. And that's what you need to do. I don't have the assignment. That's not included in the grammar. I could put that in there, but it's just another production rule. And so my little program would say, except y, except plus I might have to run it. I think it would do it this way, except z what I'm getting at now is this parse tree should have plus y, z, plus y, z. I'm confused.
Some parse trees, the notes of a parse tree are grammar production variable.
So it's going to have y and z and plus, and it's going to have m and n and plus, and then it's going to have multiply, and then it's going to have equal and x. That's the parse tree for this expression. And that's what I was trying to draw. And so what this parse tree does is capture the appropriate precedence. So it'll do this add inside of the parenthesis before it'll do that multiply. It does that multiply last. And so our grammar and your C- grammar our grammar of E goes to E plus T or T goes to T star F or F goes to paren E, paren or A or B or whatever. This is a precedence preserving grammar. And the grammar you're given in C minus is a precedence preserving grammar, unless you wreck it somehow. And students have wrecked it in the past for whatever reason. No need to wreck it. But what it amounts to is those things lower in the parse tree are evaluated first. These things higher in the parse tree are considered or evaluated later. So this plus can be done first, but this multiply can't be done until after this plus is done. Now, if it were written y plus z multiply m plus n, then the parse tree would look like this. It would look like y plus multiply z m plus an n. And so this is the lowest in the parse tree. It would actually be done first. Then this plus is next lowest in the parse tree. It would be done second. This plus is the top of the parse tree. So the pluses are done left to right with multiply higher precedence than plus. And so this is the way it will be parsed and evaluated. And so if it were in Project 4, it's essentially generating code to do these things in the proper order. That's what Project 4 does. And if you leave the grammar in its current good form, everything will come out in proper order.
I was just gonna say, on the original parse tree, should the parentheses be there? It would make it, on the original parse tree, shouldn't the parentheses be a part of it? Because it would make it lower, which would be covered first.
But it can do this addition. It's evaluated in precedence where multiply has higher precedence than add. So, and so it does it in a left to right scan. So it can do this addition. There's no precedence conflict. It'll do this addition first. And then it'll see this. And it'll do this second. Then it'll do that third. It will. You get this for free because of how this grammar is written. There isn't anything you've got to do other than make sure you don't wreck it. And there's no reason to wreck it. Kevin?
Yeah, sir. Doesn't addition have the higher precedence? So,
Well, multiply has higher precedence than add. I mean, it's
does it?
multiply and divide and add and subtract, from higher to lower.
Wait a second, I think I got confused there because, no.
Brendan?
So the first thing it does is add m and n, because that's in parentheses.
The first thing it does is add x and z.
Y and Z.
Wait,
The
Oh,
first
no,
thing it
wait.
does is add x and z.
No, yeah. No, I get what, yeah. You're saying that, but then, sorry, that's, I get what you're saying, but here you're doing the plus first. But the multiply having higher precedence means that it goes.
So I've got x plus, I've got a
The x plus,
plus b times parenthesis A parenthesis end of input. Okay? So that's out 11. And so my code gen out 11. So this is a reflection of the parser. And this is now demonstrating Project 4, which you're not supposed to understand, but Project 4 is a reflection of the organization of this parse tree. And the stuff that's put out first, is an indication of where this is in the parse tree. You write this in an arithmetic expression in C, C++, Java. The computer will compute this first, it'll add that first, then it'll add that, then it'll do the multiply. And that's what this is saying. Add this first. This doesn't look right.
Yeah.
This counters me. See, so it's saying,
You should add this before you multiply.
No,
see, this isn't right. It's, except so, well, here's the left part. Oh yeah, here, it adds this first.
Yeah, it adds that, then closes it.
Adds and then multiplies.
It's-
Then closes it. Yeah.
can I interject?
Yeah.
That's what I was saying.
That's how it should be, right?
That's what you're all trying, that's what you've been trying to tell me.
Yeah, that's what I've been.
It can't add that because this thing is multiplied.
Yeah.
That's what you've been trying to tell me.
Yeah,
All right,
I,
you are correct. And I love that, actually. That shows me you guys know what's going on. That's good.
Do we?
Now, if I wrote this though, y plus z plus w times m plus n. That's what I had in mind. Now it's going to add the y and z first. That's what I had in mind.
yeah, add them first because
It's going to add the y and z first.
they're the same precedent, so it can.
It's going to add the y. I think my program is correct.
Yeah.
And so a plus b, what was that? Plus a times, that's it, yes?
That's.
And so now it does the add first. It does the add up here, A and B. It saves the multiply, as you all were telling me all along. It does this add, then it can do the multiply, then it does the final add. This adds last. This adds first. This adds second. This multiplies third. That adds last. This program that generates this code is working off of this grammar fixed. This grammar with the removal of left recursion. And so again, I promise you, the grammar is precedence preserving as long as you don't wreck it. When we get closer to Project 4, I will show you my code generation program, my CodeGen Python program, and it should help you write some of the code generation stuff. It's not everything you need, but it's expressions, which is a good bit of what you need. Questions? Good? Thank you for straightening me out. All right, so. I mean, I think you ought to be thinking about project 2 by now.
It's on the horizon.
And of course, I'm being extremely facetious. I gave you like a month to do project 2 for a reason. And so we've got A goes to A plus, really? A goes to A paren, or empty. This is almost like we did
Test.
with LR of 0.
Yeah.
Except I had an A here instead of an empty. And so we're going to parse this now. And so we augment the grammar and we build the finite state machine. Okay? So we start out with the start symbol, with the period keeping track of how much we've seen so far. And of course, we've seen none so far. Period in front of the A says write A's rules. So, period in front of a non-terminal says write that non-terminals rules. A lot of what you got to do here is memorize the rules of how to play the game, the rules of what to do. And so that's what you do on this. So we write A's rules. A goes to period A paren, A paren. A goes to period empty, and empty is a nothing. We use the epsilon to represent a nothing. See, if we did it, I mean, that's really what I'm saying, right? But now you don't know if I just forgot to write something there, or if there's supposed to be something there. And so we use this symbol to represent nothing. It's not a blank, it's not a space, it's a nothing. I'm grabbing a nothing. Except I didn't really grab a nothing, I grabbed some air and get to hold it, but it's a nothing. All right, so we have period in front of that nothing, which is just period. Make sense? Well, and so period in front of the A, see, we wrote A's rules because period in front of this A. Now, period in front of this A says write A's rules. But A's rules for this A are identical to A's rules for this A. So we don't have to write them twice. I mean, you know, it's a set. And so I just have the same two things here again, and there's no need to write it again. You with me? So this is the name of item set 0. Then we can see an A. As we're parsing, we might end up with an A. So we get A prime goes to A dot. We move the period across the A. Well, if we move it across this A, we move it across this A as well. And so we have in here A goes to A dot paren A paren. The dot is at the end of the rule. There's nothing to move it across now. Stefan?
So this dot's kind of like the read head
is kind of like the
The
what?
read, like on a turn.
The read head?
Yeah.
Yeah, I suppose you could think of it that way. It's the marker, it is technically the marker that keeps track of how much of the right-hand side we've seen so far. Well, and so if we read it, then we've seen that, and so we move the marker over. Okay? All right, so we claim this is item set 1. And this is our accept, but this we still got to do more work on. We're still, as a result of augmenting it, we've got a unique accept configuration. All right, so then we might see left paren. We get A goes to A left paren dot A paren. So period is in front of the A. We follow our rule. And we write A goes to dot A paren, and A goes to dot. Okay?
Why'd you rewrite A goes to dot A?
Because I got a period in front of the non-terminal. Period in front of a non-terminal says write that non-terminal's rules in the item set. These things are called item sets. This is an item set, this is an item set, this is an item set. Brenda?
So when we're rewriting the rules for the non-terminals, we go back to the original grammar.
Yes.
Start at that rule and go down.
Yep. Yep. So this is like saying I can replace A by A's rules. And if I replace A by A's rules, I've not seen any of the right-hand side of those replacement rules. I'll say that all again. This says I can replace A by A's rules. A is on the left, A's rules are the right. And if I replace this A by its rules, I haven't seen any of the right-hand side of those replacement rules. So the period goes back to the front. Okay? All right, so now,
If it sees an A, would go back up to the first set?
this A, this A,
Yeah.
well, this A, yes, period in front of this A says write A's rules again, with the period in the beginning. So if I write from here, so these two rules were the result of this. So now I'm going to write A goes to dot, A paren, and A goes to dot as a result of this. But these two are identical to these two.
So would it go back up to the?
And so but if this goes back up to the original grammar, it's still identical to this.
So we have
It's an item set. Writing duplicate items, duplicate characters in a set doesn't buy you anything. Right? And so we don't gain anything by writing all of that again. So I claim this is item set 2. Good? See where I got that from? We're learning how to build item sets. Now, if you read your text, which I believe some of you are doing, your text author does the move from here to here, And then he does this completion in two separate steps, in two separate diagrams. And so this is a move to get to here, to get to just here. And then he talks about the rest of this as the closure of the item set. I think that's harder. I mean, just do it. Do it all at once. It's easier. Okay, then we move here on A. And so we get A goes to A paren A dot paren. And if we move across this A, we don't really know if it's this A or that A, so both A's move. And so we get A goes to A dot paren A paren. From here to here. Item set 3, period not in front of any non-terminal. So there's no rules to add. We can see a right paren. We get right paren, we get A goes to A paren dot. Item set 4.
Could you also see a left paren there? Would you go back?
Yeah, I'm not done. I gotta do left paren as well. Jeffrey?
Why in item set 4 do you not rewrite the second rule from item set 3?
Well, because we're moving on this symbol. This, which we would move on, is a different symbol. And so we would add to it a left paren. A goes to A left paren period A right paren. So we need that move too. But this symbol and that symbol are different symbols, and so each arrow in our finite state machine is labeled with one symbol. It's a deterministic machine. Now what?
Write A's rules.
Got to do the closure or finish off A's rules. So A goes to period A paren, and A goes to period.
Now it's the same as item set 2.
And so that looks like item set 2. And so we do these things in chalk or pencil. And so we write left paren, and we take our way cool eraser. You with me? Not going too fast?
You're erasing too fast.
Erased it too fast. Well, and if you don't recognize identical sets, this will go forever. You must recognize identical sets. All right, well now, this one's done. I moved on A, nowhere to go here. This one's finished. I moved on left paren, nowhere to go here. This one's finished. I moved on A, nowhere to go from here. This one's finished. I moved on right paren, and I moved on left paren. So my finite state machine is built. Okay?
So.
Now, where we're going on all of this, where we're going on all of this is that we are doing an SLR of 1 That's what we're targeting, that's the technique.
Listen through this.
Okay, good. Is this grammar now LR of 0? Is it capable of being parsed with the LR of 0 technique?
No,
No, why not?
because of the dot, nothing.
Because these imply shift, and this implies reduce. And so the parser does not know what to do. This one is also no good. This implies reduce. This one implies shift. Also no good for LR of 0. Also no good, these two imply shift. This implies reduce. This one actually is good. This could be an LR of 0 state because it implies shift. This one is actually good. It could be an LR of 0 state because it implies reduce. But with the other conflicts, if any state has a conflict, then the thing is hosed. Okay? So, how do we resolve the conflict? We resolve with, which you all know and love, dearly. You love it dearly. First and follow sentence. So we'll compute first of A prime A, and we'll compute follow with a little more space. We'll compute it down here, follow of A prime and A. So, the first of A prime is the first of A. The first of A is the first of A. The first of A is empty. Okay? So we get an empty. Since the first of A is empty, this A can go away, so it can generate a left paren first. The first real token can be a left. Well, you know how to do first and follows, right? And so I can get a left paren as the first of A. Well, and so the first of A is the first of A prime, empty and left paren. Okay? Then we do follows. Dollar sign. Then we say the first of right paren is in the follow of A. The first of left paren is in the follow of A. The follow of A prime is in the follow of A. The follow, no, I can't do the follow of A into this. Remember, we do firsts, and of course, terminals don't have follows because they can't go away. Remember, we do all of this just because of the empty. Well, and so then the follow, I can't do that because again, right paren doesn't have follows. But the follow of A prime is in the, well, you know, again, you know how to do follows. All right, so that was a little review. All right, so we arguably could parse now. But it is generally accepted in all compiler books that you build a table to capture the first and follow sets and the finite state machine. So the table is a union of those things. They put them together to guide the parsing. And so the table is built with item set numbers as row labels and grammar symbols as column labels. And so this is the construction of this table. In some respects, of course, it looks like the top-down table, but the top-down table is built differently than the bottom-up table. And also you should react. We're doing bottom-up, we're doing SLR1 parsing. I never worried about the left recursion. Left recursion is not an issue for bottom-up because we're taking this and replacing it by this. We're going that direction, whereas with top-down, we were going the other direction. Make sense? So you gotta love this. It's so pure, it's so, makes sense, it's so good. It's not like, I told my wife last night that I bashed her English. Did I bash it in here or system software?
You did.
In here?
Yeah.
Yeah, well, I told her I did. And she says, okay, well, where did you learn to speak? I said, I learned to speak like a baby listening to my parents. And she says, oh, okay. Where did you learn to write? I says, oh. So we fill out the table off of this information. Item set 0 goes to 1 on A. And so 0 goes to 1 on A. That takes care of these two. Item set 0 reduces A goes to empty. That is, the empty is replaced by A. We pop nothing and we push an A on the follow of A. And so we write empty, empty, empty. And that implies, and you can write it like this. A goes to empty, A goes to empty, A goes to empty. That's the action from item set 0. You reduce you reduce empty to A on the follow of A. Okay? Now, what your text does, again, what your text does is they number these. So we have 3 rules. And so if you're studying your text, you know, I don't want you to be confused. Dr. Egan did this in class and the text does this. The text will write a 3 in here. And I don't remember, I don't think they even write the R, but it means reduce by rule 3. Okay? And so I've captured item set 0. Row 1. Row 1, we reduce on the follow of A prime. The follow of A prime has $1 in it. So this is our except configuration. As a result of augmenting the grammar, the follow of the new start symbol will always only have $1. So when we parse and we see that $1, we know we're done. So item set 1, reduce on $1, that's our except. Left paren says On row 1, you can write anything you want to in there. I mean, as long as it makes sense. Adrian?
So why did we do RD again? Just because of the,
Well, this is rule 3. A goes to empty, okay? And the period is at the end of the rule. So, I wrote this Tuesday, I think. Period in the middle of a rule is a shift or go to. Period at the end of a rule is a reduce. Those are the rules. If it's an entry
Yeah.
under a terminal, it's a shift to. If it's an entry under a non-terminal, it's a go to. And so these columns are go-tos. These columns would be shifts. Your textbook actually calls these action. I don't know why action. Shift makes sense to me. Again, some of you, I assume, are reading the text. If nobody's reading the text, then I won't bother with all they say. I think you ought to read the text. I'm doing what Loudon does. I'm doing what A. Hohenholman does. That's another compiler text that does the same stuff. Actually, A. Hohenholman and SETI. There's another one too. Barrett, I think. I forget his name now. Anyway, item set 3. Shift 4 on right paren. Shift 2 on left paren. Okay, item set 4. Reduce by rule 2 on the follow of A. And so right paren, A goes to A paren A, or rule 2. I actually don't like writing both of them in there. What do you want me to write? Reduce by rule 2, or you want me to write the rule in there?
The rule.
Write the rule. Reduce by A goes to A paren A paren. Reduce by A goes to A paren A paren. The follow of A. The period is at the end of the rule. And so I can pop this off the stack and put that in to parse. That's what that's saying. All right, we have built the table. Stephen?
Can you explain how you got the accept under the $sign column?
Well, right here, the period is at the end of the A. That would normally imply a reduce. But this is our augmented start symbol. And so if we reduce to it, it's where we have processed all of the input, so that's why we accept it. We will always, since we augmented the grammar, we will always have one of these. That way we're guaranteed to know when we're actually finished parsing.
Just want to clarify this, the difference between the go-to and the shift to, or shift to, like the difference between shift 2, shift 4, and like just having 1 and 3 in the other column is the fact that it's reading a terminal versus a non-terminal.
It's guiding the
dots
parser.
moving is like only, yeah,
Yeah, it's guiding the parser.
yeah.
You'll see the difference in the how we parse and the actions.
Yeah.
All right, and so that's what I'm going to do now. That's what I'm going to do now. I am going to
Or sorry, again?
Uchi,
Could you explain how you got S4?
I'm sorry?
Shift 4.
Shift 4.
That's this line.
No.
That's this line.
Okay.
This state moves to this state on that terminal. When you move on a terminal, it's a shift. If you move on a non-terminal, it's a go-to,
Yeah.
as opposed to a shift. Okay, good? All right, so I claim dollar might be an input string this grammar can generate.
Yes.
It might not be, but our parser will tell us. Fairly easy to claim that. All right, and so we have $0. So this is my stack. My stack lays down, and this is my current token. I'm doing SLR1, so I get to look at the current token, as opposed to the dumb LR of 0, which didn't let me look at the current token. The LR of 0 is only presented to you to guide you in the building of the finite state machine. It's not meant as a parsing technique per se. It just shows you how to build the finite state machine. The finite state machine is used in all parsing techniques in one form or another. Mostly in this form with a little addition. Okay, with me? So LR of 0 said we know how to build a finite state machine. SLR of 1 says we get to look at the current token. And now we parse like we did on Tuesday. So I look at row 0, column left paren. Row 0, column left paren says reduce A goes to empty. So I pop off the empty and I push on an A. So I get $0 paren, dollar. I popped the empty and pushed on the A. I reduced A goes to empty. Now this is the only hard part of this whole process. This is non-intuitive. I struggled with this for years. I look at the 0A, I always gotta have a state name. A 1, 2, 3, or 4 on the top of the stack. 0A says I'm in state 1. So not only did I do, or as part of the reduce, I look at where I go to. So as part of the reduce, I go to on the table. So in some respects, I did 2 steps from getting from here to here. I popped and pushed my stack, that's 1 step. And then I go to. I always got to have a state name on the top of my stack. Okay? Now I look at 1 left paren. 1 left paren says shift and go to state 2. So I get $0A1 shift state 2. The parsing that we're doing now is in essence the same as the parsing we did Tuesday with the LR of 0. But we got the table to help guide us this time. Two left paren. Two left paren.
So left print 3.
Two left paren. Two left paren. Reduce 3. Pop the right side, push on the left side. So I've got $0 A1 paren 2.
A.
Pop it, push it,
Shut.
and 2A.
Yeah.
Paren, dollar. Okay? 3 left paren. Shift 2. $0 A1 paren 2 A3 shift 2. Two right paren. Two right paren. Reduce 3. Reduce A goes to empty. $0 A1 paren 2 A3 paren 2. Pop the empty,
Push an
push the A,
A. Go to 3.
paren, dollar. 2A, I'm in state 3. Okay, cool. Stop me if I'm going too fast. Alejandra, did I pronounce that right? No? I thought I had it. I'll keep practicing. Mike, did I pronounce that right? I get some of them right. Good? So now you gotta tell me after class or tell me sometime how to pronounce your name again. 3 right paren. 3 right paren, shift 4. So I get $0 A1 paren 2 A3 paren 2 A3 shift 4. Paren, dollar. The stack grows, the input shrinks. William? Good? I remember, I learned William today. And I learned, I sort of knew Jeffrey before. Jacob, I think. Jacob? He's Pennsylvania. Either that or it's the wrong man. 4 right paren. 4 right paren. Reduce all this stuff. So I got a right paren, an A, a left paren, and an A. So I've got a right paren, an A, left paren, and an A. So that gets me $0 A1 paren 2. And I pop all that off, and I push its left side on, who is an A. Then I look at 2A and it says I'm in state 3. 2A, state 3. And I've got paren, dollar left. 3 right paren. 3 right paren, shift 4. Adrian?
How did we get A3 again in the last one?
Just what we just did.
Well, so I popped all this. See, I was right here. So I popped all of this, I pushed that on.
Oh,
What we're doing is we're reducing right-hand sides to left-hand sides. Again, if you read your text, they call these things handles. I never did figure out why they call them handles, so I don't talk about that. We're reducing right-hand sides to left-hand sides, and we're recognizing the right-hand sides. Okay? 3 right paren says shift 4. So $0 A1 paren to A3 shift 4 paren dollar. 4 left paren says reduce all this stuff. So reduce paren A. So I get $0, push the A on. I've got paren dollar left. I've got paren dollar left.
and you go to 1.
Dividing input from stack. 0A says I'm in state 1. One left paren says shift 2. So shift $0 A1 shift 2 paren dollar. It's essentially easy now. All we're really doing is what we're told. Do the table lookup. Do what you're told. And what you're told is this stuff. Well, it's really this. Or really this. 2 right paren. 2 right paren. Reduce A goes to empty. Reduce empty to A. So I get $0 A1 paren to A right paren dollar. I popped off the empty and I pushed on an A. 2A, I'm in state 3. Three right paren, I said shift 4. $0 A1 paren to A3 shift $4. $4 says reduce all of this good stuff. Reduce paren A. So I get $0. I took off the right-hand side, I push on the left-hand side. A. 0A, I'm in state 1. Dollar input. $1 accept. Uchi.
I just wanted to clarify, when you're shifting and reducing, you don't shift the states, you only shift the non-terminals.
What do you say?
You say you don't shift the state, you only shift the non-terminal.
Well, so what did I do? I shifted shifted the terminal on, and then I went to the state that it tells me to. The S2 says shift the terminal onto the stack and go to state 2. So I'm doing two actions essentially at every move. Shifting it on and going to a new state. I'm guided by my finite state machine. So I'm making moves as defined by the finite state machine.
So like in line 6 or something, where we see 4 for left
For here,
no down.
No.
Yes.
There.
So 4 says take everything else. For
yeah, so I'm looking at the 4 and the right paren. I always look at two things because I'm doing a table lookup. So 4 right paren.
Yeah.
And so when I write the production rule in here, the period was at the end of the rule. When the period's at the end of the rule, I do is reduce. And so I've recognized all of this right-hand side, and I'm replacing it by its corresponding left-hand side. So I pop all of the right-hand side off of the stack, and I push its left-hand side on. So that took all of this off, popped all of that, and pushed this on. And then I looked at 2A, that told me to put the 3 in.
Okay. I was just confused. I thought the same 2A was the same 2A from the first step. What is it different?
Well, so 3 right paren, 3 right paren says shift and go to state 4. So I shifted the right paren on, and I went into state 4. Sonia?
So we only have one, or whenever we augment our rule and we reduce it, that's our only accept state.
Yes.
But for any other state, when it's fully reduced, that's just a reduced state, it's not accepted.
When the period's at the end of the rule, it's just a reduced state, yes.
Okay.
Yes. By augmenting, you don't augment the rule, you augment the grammar.
Sorry.
That's the correct terminology. And so when you augment the grammar, that will force a unique accept configuration.
Always.
Always. It will always force a unique accept configuration. Jim? That's what I said. We had a fellow whose name was Yap Chua. He was faculty here. He retired about 6 years ago. So one day, everybody called him Yap Chua. His name was Y-A-P-C-H-U-A. C-H-U-A was his last name, Y-A-P first name. So everybody called him Yap Chua. And so finally one day he and I were talking. He says, you know, my name really isn't Yap Chua. He says it's Yap Chua. And I said, oh, okay, good. I'll call you Yap Chua. And he says, no, Chua. And I said, Chua. And he said, no, Chua. I absolutely couldn't hear the difference between what he said and what I said. I swore I was pronouncing it exactly like he said. So, Jim.
On the second line over there, how'd you get A3 after the left turn to? Up. No, second.
Down.
One more. Down.
Yes.
Yeah, from here to here.
Yes. How'd you get A3?
Well, so 2 right paren, yes?
Yes.
2 right paren says reduce by A goes to empty. So I popped off the empty, which is a nothing,
Oh.
and I pushed on the A. And then I read 2A, and I put on the 3.
This is fun.
So, are you good at this?
With more practice.
We have a quiz?
Well, so what do you want me to do on Tuesday? We have 2 choices. What I have just shown you is SLR1. The next step is the next parsing technique, which is LR1. What changes is how you build the finite state machine. You build the table much the same, and once you've built the table, you do the parse exactly the same. And so if we move forward, you'll learn more stuff about how to build a finite state machine. I think maybe we ought to spend another day doing this. So I'll do, on Tuesday, I'll do another SLR. And then Thursday a week, you'll have quiz on SLR stuff. Okay?
I claim you left that on the board, then gave us a test.
If I left this on the board and gave you a different grammar,
Yeah,
then you could do it?
yeah.
Yes.
So you all get a 3x5 card, which isn't big enough to put all this on. But you can put enough on your 3x5 card to give you hints.
Yeah.
We can fit this on.
Get it on there?